Hey everyone, and welcome back to this class, Advanced Convolutional Neural Networks. In this lecture, we are going to talk about how to deal with different sized images when training a neural network. This is a really practical question since, as you know, images on the internet come in all shapes and sizes. If we're going to build an AI that can learn to recognize things in images, then a prerequisite to this is handling images of different sizes. What you'll find is that the solution to this problem is rather simple. So recall the basic architecture of a neural network. We begin with a series of convolutions and we end with a series of dense layers. What happens at the interface between the last convolution and the first dense layer is that we flatten the final output image. Let's say it's of size 5 by 5 by 1024. Then the input dimension of our first dense layer must be 25,600. So where does this break down? Well, the final image size is always dependent on the size of the input image. The key point being everything up to and including the final convolution will just work, irrespective of the size of the input. For example, if you have a series of 2 convolutions with a stride of 2, and your input image has length 32, then at the end of those 2 convolutions, the image will have length 8. But if your input image has length 28, then the final image will have length 7. So the problem is the final image can have different heights and different widths, depending on the input shape. The solution to this then is to use an operation that yields the same result no matter how tall or wide the image is. We call this global pooling. There are 2 variants, global max pooling and global average pooling. Both behave analogously to their non-global versions. So global max pooling will look at a 5 by 5 by 1024 image and output a 1 by 1 by 1024 image, where it's just taken the max over the height and width. Global average pooling will look at a 5 by 5 by 1024 image and output a 1 by 1 by 1024 image, where it takes the mean over the height and width. This way, it doesn't matter if the output image is 5 by 5 or 6 by 6 or 7 by 7, it always gets shrunken down to 1 by 1, and only keeps the feature map dimension. Implementation-wise, in Keras this is very simple. They are just different layer types called global average pooling 2D and global max pooling 2D. In TensorFlow, you could just use reduce mean or reduce max, or in other words, you don't need to think of it as a layer at all. So why does this work, and why is it okay to just take the whole image and squash it down into 1 pixel? Well, we've discussed this before, but it's worth repeating. A CNN finds more and more global features the deeper you go into the network. This is simply because the image itself shrinks. So in the very early layers, a CNN will find very detailed, tiny edges, then progress onto broad strokes, and then finally to big objects like animals and vehicles. Thus, by the time you get to the end, the image itself has gotten so small that the features are more or less global, and you can take the max or average to give you some translational invariance. In other words, it doesn't matter where in your image there was a cat, we just want to know, was there a cat at all? And by the way, you can apply this strategy to any of the pre-trained networks we used in this course, such as VGG, ResNet, Inception, and others. Typically, we just chop off all the fully connected layers and connect our own.